That's good. Okay. I probably don't need a mic. My voice is very booming, my wife tells me. I am Slav Hermanovic. I am on faculty at the Environmental Engineering Group here on Berkeley. And Linda Vida, who is the director of Water Archives, asked me to host this colloquium. Linda is enjoying her vacations, long-term planned vacations. So I wanted to welcome you to the third California Colloquium on Water. This is our penultimate colloquium in this this semester. December 4th, we'll have a talk by Professor Charles Benton, Professor of Architecture, entitled A Camera Aloft, California's Wetlands and Streams from a Bird's Perspective. So this should be really exciting visual presentation. I understand that he flies kites to take photographs. I wanted to say that this colloquium is sponsored by a number of campus and off-campus groups, and we appreciate the sponsorship, particularly the deans of the College of Engineering, the College of Natural Resources, Architecture, and the Humboldt of Law, the Beatrix Farron Fund of the Department of Landscape Architecture, and also the Earth Science Division of the Lawrence Berkeley National Lab. So this is a great sponsorship of this event. As I said, there will be one more event this semester. There are brochures at the back of the room if you want to take one with you if you don't still have it. And there's also supposedly a sign-up sheet if you want to receive email reminders about this. Now, without any more talking, I would like to introduce Lisa Alvarez-Cohen. She is a colleague of mine, and she's a professor in our department, as well as the chair of the department. And it has to be all very layered, so she will introduce today's speaker. There is a special connection between them, but I will not tell anymore.
Thank you. Thank you, Slav. It is my distinct honor and pleasure to be able to introduce Perry McCarty. And the reason I'm able to introduce Perry is because he was my mentor and my PhD advisor. As a matter of fact, I remember being in graduate school and getting my master's degree and saying, there is absolutely no way I am staying past my master's degree. And then I got to know what Perry was doing and observed him and the fun he was having and the knowledge he was generating. And I realized through that year, I turned around and said, Perry, the only way I will continue on to get my PhD is if you'll take me as a graduate student. He said no a couple of times, but then eventually he relented and let me stay. I want to tell you a little bit about Perry's background. He got his undergraduate degree at Wayne State and then went on to MIT to get his master's and his doctorate. And then he had a little stint in the military, serving his country. And then he was lured out west by an offer at Stanford. They were smart enough to recognize what MIT had, and they brought him out and they offered him all kinds of things. It was a great startup package, right, Perry? I love hearing you tell that story. And he's been out at Stanford ever since. And I have to tell you, his career at Stanford has been unbelievably stellar. Perry has won every award there is. Oh, first of all, I should mention, he's known as the father of environmental biotechnology. And in fact, to prove that, he's written the ultimate book on environmental biotechnology. We use it in our grad course here at Berkeley. It's a terrific book. He's also written other books. He's also written hundreds and hundreds of research articles. He's also won every prize there is, the Tyler Prize, the Clark Prize, and then this year, the Stockholm Water Prize. Fantastic. There are great pictures of him in his tuxedo getting it from the king in Sweden. Very exciting. At any rate, Perry McCarty is also known in the professional circles as well as in the association circles. He's a fellow of all of the academies, National Academy of Science, National Academy of Engineering, American Association of AAAS, that one. He's a fellow of the American Society of Microbiology. Everybody wants to have a piece of Perry McCarty, and he'll show you why in a minute. I was going to finish this introduction up by showing you a super secret long-term experiment that was conducted by the federal government in the late 80s because they were wondering why this Perry McCarty fellow was being so successful. And unfortunately, it was actually termed the evolution of Perrius McCartius. Unfortunately, I have pictures from each of those years that look phenomenal on my Macintosh computer. Just beautiful, impressive. As a matter of fact, this one right here, the 1989 picture of Perry McCarty has him with a full bicycle mustache that was painted on with black lipstick. He looks phenomenal. One of them, he has pink glasses on and a blue Hawaiian shirt. And then the last two are showing him winning his most recent prizes. And I'm sorry they're not showing up here. I apologize for the computer glitch. But I give you Perry McCarty.
Thank you, Lisa. I'm glad your computer doesn't work very well. Pleased to have an opportunity to be here at Berkeley again for a seminar. Lisa indicated that she wanted to be a PhD student with me. And I said on one condition, she's got to say good things about me if she ever gets to introduce me. So she's passed her test. Thank you, Lisa. Oh, sorry. So I get to talk with that working? Okay.
Sounds good.
Okay, and then I push that.
Which one is yours?
Which one is mine? Good question. Where to go to? It's not this one.
Okay.
Somehow I gotta get this thing out of here. So if I can get you up here. There we go. Okay, now I gotta see if I can work a Mac. I mean a PC. I have a Mac as well. There it is. That right there? There we go. Oh, this thing's going to forward. Thank you. I started doing research in this field a few years ago. In fact, it was exactly 50 years ago that I finished my master's degree and started conducting research in the environmental field 50 years ago this year. So this is a golden anniversary for me, if that's... and at that time, when I started my research, these were the major problems that had been addressed, and in fact, they were pretty major problems. I wonder if these front lights can be turned off. Is that possible? They're sort of shining on the screen. And the pathogens, we were doing a lot about them in water, oxygen depletion, industrial waste, and nutrients, which we still got problems with them, but they were major problems at that time, and we were just beginning to address them when I started. But there was one problem that was new, and I did some of my first research. My professor, Claire Sawyer, was working on this, trying to convince the field and the manufacturers that this problem that we're finding was due to synthetic detergents, new synthetic detergents. So our treatment plants all started looking like this. And this happens to be San Jose, new San Jose treatment plant. Thank you, that's good. It was shortly after, actually, my professors at MIT, Claire Sawyer and his students, discovered that the problem with the new detergent molecule was that it was fairly branched. They said if you straighten it out, the problem will go away. Manufacturers resisted that, but by 1964 they did change, and that problem did go away. Nice, simple solution. Well, at that same time, we had another major problem, which I want to talk about. Chanute, Kansas, we had a drought. Water stopped flowing in the river they used for the water supply, so they put a dam. The wastewater then backed up to the drinking water supply, and this is the water treatment plant, where they had all that suds foam going on. And so they tried to treat it the normal way we did it at that time. And the nice outcome on the right there was the drinking water had a nice head of foam, but it didn't taste so good. And so we had to do something about it. So this was really a start of our thinking about reusing wastewater in the growing need that we were going to have in the future. Fortunately, others were thinking of this. This is at the Los Angeles County Sanitation District's Whittier Narrows was the first plant that was planned to reclaim wastewater. And in here, they put it into spreading basins and let it percolate down to the ground so that whatever might have been left, because now we're concerned about trace organics and these persistent organic pollutants that we know now, and they felt that the soil would handle that as it percolated down to the groundwater. And that's still successful. We felt that there was a need to go further than that. And here back just in 1965, CH2M Hill, a new company that was formed for a professor and his students at Oregon State, and Claire Hill, who was one of our graduates who had a little firm up north. They got together and built the first really advanced treatment system addressing this new problem that occurred just a few years ago. And here they went through biological treatment and then chemical treatment in the tank you see there. Air stripping, first time air stripping, therefore ammonia removal. Went through multimedia filtration and then finally through the activated carbon canisters you see on the right. Complete treatment at that time. Now this was more of a demonstration, taking it full scale, that now we could do it and address problems. Unfortunately, that came at a time because it was just a couple years later at Windhoek, South Africa. The same thing happened as the Chinook, Kansas. They essentially ran out of water. And so they had to use, the only source they had in this very desert area was the wastewater. And so Jerry Stander in South Africa brought in the technology, and if you see in the upper corner is the treatment plant, and way in the back you see those tanks, they're activated carbon canisters, removed the final organics, and then it came on the same site directly to this water treatment plant you see here. It's fairly small, but a water treatment plant went through the normal water treatment plant and went to the community. So that's a pretty direct potable use, which we still are kind of feared of having in this country, but it was an important at that time as an advance, and still is, to meet the growing need for water and the shortage in many parts of the world. Well, you know, it wasn't that much later because of this growing problem, the need in Southern California. Certainly California is where we have real problems. And so Water Factory 21 started in 1976, Orange County Water District. And they went one step further than we saw there. They went to reverse osmosis, which you see on the right. So essentially moving all the salts from water. And they called that Water Factory 21 in 1976, and they were right. And we know today that this is the technology that's being applied throughout the country here. Membranes have really become on. This was the first really good demonstration of large scale, about 5 million gallons a day, reverse osmosis membranes. Proved greatly since then, bring the cost down, and it is the state of the art. One big problem with this is it does help us in the water, but it takes a lot of energy. It takes a lot of energy to pull it through. And now that's creating a problem. We think we can get water, but it costs us energy. And certainly if you went to seawater, that would be true as well. There's a big energy cost to it. And that kind of brings me up to another point. When we have the high energy costs, we have the deficiency of water. And although we are doing great things with our technology, we still have to face the fact that over 1 billion people in the world don't have access to safe water. So like this woman here having to carry water a long distance, and the water is unsafe, taken from an open well where people are bathing and so forth. So that's a major problem, yet in half the world's people do not have adequate sanitation. So while we've come a long way in some sense, we still have a big problem, and a problem that's going to be made worse in coming years. And this goes back, starting thinking about this, again, when I started 50 years ago. Dr. Charles Keeling, who's at UC San Diego, was brought on by Roger Revelle, who believed in what he was talking about when he was when Keeling was a youngster. They were looking at the carbon emissions from fossil fuels and saying, you know, they really have an impact on climate, can have an impact. The greenhouse gas effect was talked about. And so Keeling got sensitive measurement of carbon dioxide, went to Mauna Lea mountain in Hawaii, and started taking these measurements. And they're really nice measurements because you see that yearly variation. In the summertime, it sucks up CO2. In the wintertime, it goes back. So you get this yearly variation but it's going up. I first saw this curve in 1968 and first heard about it, and they were saying it looks like it's going up, and so people began talking about it then and wondering what the future holds. And it is finally now that we can see that trend continued, in fact it's accelerating, and now we have really concerned. And part of that, just this year, the Intergovernmental Panel on Climate Change, which started several years ago trying to address this problem, seeing what the science behind it was, a lot of skeptics, and they finally this year came out with a report in 2007 saying that the observed increases that we're having in temperature throughout the world is very likely, and to them it means a 90% probability, is because of anthropogenic, our greenhouse gas emissions. This group, as you know now, just a few weeks ago with Al Gore won the Nobel Peace Prize for bringing this scientific evidence to the attention of the public as well as to publicizing the importance of it. Other part of this that I'd like to point out is in their report, they indicated it's not only carbon dioxide, which we generally hear about all the time, but also methane and nitrous oxide are the very likely to have been on the changes unprecedented in 10,000 years. And that's essentially the whole time of human civilization since we started gathering together, 10,000 years. And they produced these graphs that show that one in the upper right-hand story of carbon dioxide, 10,000 years. And you see in the last 150 years, all of a sudden, it shoots straight up. And it's showing the little insert there of that last 150 years since 1800. You see it's about the last 50 years, and it's accelerating because we are continuing to use fossil fuels faster and faster in greater amounts. I want to also point out we get the same picture with methane and nitrous oxides. And that have a lot of implications on what we as environmental engineers do. I want to talk about that. But here's the global changes that they're showing in the IPCC report, that temperatures, at least in the past 100 years, and primarily in the last 50 years, have increased about 1 degree Celsius. The oceans have increased about almost a foot, and we see the snow cover throughout the world is on decline as evidence of the impact we're already having. And very interesting here, which is I found really surprising, is that the Supreme Court, this is Wall Street Journal, and this is April 3rd, not April 1st, not an April 1st joke, it's true. Supreme Court said, essentially, go back, that carbon dioxide and other greenhouse gases are air pollutants. And that's a real change for us in our field, that my gosh, all the time, everything we did, if we could take all these organic materials and get them to CO2, that was our objective. And now, all of a sudden, we find, hey, that's a pollutant too. And so it's going to, I think, cause a no paradigm shift in our way of thinking about what we do in the water field. Now, if we look at the overall balance here, this is the gigatons of carbon equivalents in an annual flux. We see most of it, what's going on, of course, is natural. What we do, the anthropogenic, is that little 7.2 over the right side. That is what we are, at least in the year about 2000, we were contributing. And that's the number that is going up, and we want to try and bring it down. Well, it looks kind of small compared to all the other fluxes. The atmosphere has about 730 gigatons of carbon, so this represents about 1%. But a lot of that partitions down into the ocean and taken up by land. So it's not the net increase, but we keep on putting it up there, and it's upsetting the balance so that it has to respond to it. So what we're trying to do is to get that 7.2 down as low as we can, or at least if we can slow it down so we'll have time to adapt. And it's pretty obvious that there's no way we're going to get rid of that 7.2 unless things really change. But if we can slow it down so that we have a chance to adapt to the major changes that are going to take place on the distribution of water throughout the world, as well as the other problems of seawater rising and intrusion into our coastal areas and contaminating our groundwater with seawater. We've got a whole host of water problems that are going to be associated with this that we have to address. And the thing I want to talk about is we can see what problems are going to be created for us in our field. But the question I want to ask here is, what is the impact of our waste and waste treatment on the greenhouse gas emissions? In other words, what are we contributing to the problem? We may be affected by it, but we're also contributors to it. Now, if we look at the global warming potential, where CO2 is 1, what we see is methane is 21 times worse than carbon dioxide, and nitrous oxides are 310 times. So while the evolution of methane and nitrous oxide may be relatively small, because of their much greater impact, they are something of more concern. And they are something that we've got to concern ourselves with. Here, the EPA did looking at the global emissions of greenhouse gases, and they estimated, well, we hear a lot about the CO2, methane and nitrous oxide represent about 1/4 of the emissions come from these two gases, 1/4. Now, about methane, I like methane. I started my research on anaerobic treatment, production of methane. I always thought it was a wonderful process. Here we take a waste, and here's just I want to just show you this, because where does a lot of that methane come? It comes from this process that I like so much. Let's follow through. What it involves, we take complex organics, proteins, carbohydrates, and fats, mixtures of organisms, feed on that, microorganisms, feed on that, convert it, hydrolyze it, ferment it, and they end up cutting it down until they convert it to acetic acid and hydrogen gas. About 1/3 of it goes to hydrogen gas, and about 2/3 of it go to acetic acid. And then the methanogens take those hydrogen, and they convert it into methane gas. So we have this ecological system of growing organisms symbiotically working together, living on our waste and growing on our waste. And for us, producing something of benefit for us. We're producing a biofuel, a gas that's not fossil fuel. So we're in symbiosis with them too, because they work for us. They work for themselves, but they also work for us. So it's a great process. However, if we let that methane go and escape, it creates a problem, global warming. So what we've got to do is capture this process and use it for our benefit rather than harming ourselves. And that's part of the problem we've got to do. Now we do this, they have shown digesters, different kind. The 3 on the left are treating sewage sludge. One Lake Tahoe and one is San Jose. And this is one of the eggshell ones. We've got a lot of them in the US now. They're in Germany at the time. And the 4 on the right are treating industrial waste. That's a winery waste in South Africa. And the upper right is a pulp waste in the Netherlands. Lower down here is a molasses waste from rum manufacturing in Puerto Rico. And the far right is a sugar beet waste in Sweden. They're all different processes. One is called the Clarigester, and over there is an upflow sludge blanket reactor. This is an anaerobic filter, and this is like an activated sludge. There's many different ways of doing this. From the outside, they can't tell much about the difference, but they're quite different processes, and they're working quite well, applying it in their particular ways. Also, China, little backyard. They got a couple pigs out in the backyard. There's many in these little villages. They have a little trough goes down below, and below it's a little 1 cubic meter tank like this, and the methane gas goes on a little pipe like this into the kitchen. I use it for the heating the stove and for lighting the light. So we can do it on a big scale, we can do it on a small scale, and all converting waste to methane. And here we're using it for our benefit and not losing it. Now, if we look at the part that's lost of the non-CO2 emissions, we can see in the world where they come from, methane and nitrous oxide, and from the US. Now the US, that don't imply the US is not doing more than its share. What it is US uses so much fossil fuels, carbon dioxide, that our total percentage in the United States of methane and nitrous oxide is smaller than the rest of the world. The rest of the world doesn't use fossil fuels. But nevertheless, in either case, this is a pretty big percentage. And just to show where the methane and nitrous oxides come from, we start at the bottom in the blue with the fossil fuels, and that's from coal, that's from sort of fugitive emissions from coal mining, from natural gas usage, and so forth. So some of it does come from fossil fuel source. But the rest of it comes from that process I indicated before, the biological process. From rice fields that are anaerobic at the bottom, enteric fermentation, that's belching from cows. That's because they have a rumen in themselves, a little digester, and some of the methane that they produce escapes. So it's a factor. Other agriculture, a lot of that's from fertilizers and the nitrous oxide that escapes. And the top is waste. Wastes are the things that we sort of are, in our field, are taught to deal with. So what we deal with, represented for 3 or 4%, are waste. Now let's look at the waste a little bit to see what's happening here. And half of that, almost or so, is solid waste. It's the stuff we throw in the dumps and and it ferments and produces methane and it just escapes. Manure comes from animals, not the belching. Now this is not the belching part, but this is the other part that falls around and it goes anaerobic and so produces methane. And the upper part is from wastewater throughout the world. Now that is not from the treatment plants, that's not from the ones I've been showing you. What that comes from is things like septic tanks and septools, where we don't collect the methane, where we put it in an anaerobic environment, coming up from sewers. So there's a lot of our waste that we don't really treat in a way where at the moment we're collecting. I think we have to do something about that. So that's kind of the bad methane that we have. So these are our responsibility. We treat manure, right? We can do that. We know how to do it. Anaerobic digesters, we can shoot that. We should. Well, indeed, last week, Tuesday last week, full-page ad in San Jose Mercury. It looked like that. Right in the middle of this big full-page, they had a little tiny picture. And so I'll blow that little picture up so you can see it. And it's talking about that little brown thing behind the cow, not the cow itself. It says, that's manure. That's gold. This is by PG&E. They're saying that down here. Find out how cow power works. Cow power, one more way to fight global warming. And so they're pushing it. They're pushing it. So we're seeing this all over. They're pushing it. Come on. We can get the cow manure and make the energy out of it. And we can do it at treatment plants. So more of this is going on. And we know how to do it. So we should be involved in that. The other thing, interesting part of the energy part is that California was looking at water-related energy use in California. It's kind of interesting when they put out the report that says, of our electricity, all electricity we use in California, 18% of it is water-related energy consumption, and natural gas over 30%. Wow. But then you look at it a little carefully and say, well, most of it's heating and cooling. In other words, we got water used in heating and cooling of our buildings, and I'm not sure, if we didn't use water, we'd use something else probably. So I don't know, maybe we can't be blamed for that, but it's part of it. Then there's other end uses, but there is a part that falls into our realm, and that's the bottom one where it says transport and treatment. And we see most of that, not much natural gas, most of it's electricity, and most of it's for pumps and so forth. Transport and treatment. But it's still 5% of electric use in California. And if we look at this a little bit, we see a difference between north and south. One of the things we see in the south, we look down below here, in the north, we only use about 1/3 as much electric energy for our water as they do in the south, South California. And it's obvious, you look up here, it's because in the south they don't have water and we have to transport it so far. We have to transport it over mountains and so forth. It takes a lot of energy to get it there. And that's another problem we've created. We've created, because we're growing, people are going away from the water, we got to transport it. It takes a lot of energy to get it there. And that's affecting global warming, and it's going to affect distribution even worse than it is now. If we come down, water treatment doesn't take too much. Water distribution, because we got to pump it to the houses. It's about the same in Southern California as here. That's a big one. But interesting, wastewater treatment takes a lot of energy by comparison. But wastewater up here, that is our major water, when we talk about treatment and transport, is for wastewater treatment. So let's look at that a little bit. Now, I've been talking about this, and some of you might say, gosh, he's talking about 1 or 2%, and we got the big problem for us. Why should we worry about it? It's not our, we did our part. Well, I'd like to, Rene Dubos, a biologist, environmentalist from back in the 70s, and he was very optimistic about it. But what he preached, and we know that, we've heard that, think globally, and we know there's a big problem globally, well, act locally. In other words, we got to all do our part on this problem. And what I want to show is what I mean by our part, because if we look at the overall problem, we may have that little piece up the top, weighs 3%, and maybe we use a little bit of that electricity. But it's all broken up into little segments. And if each segment doesn't do its part, we won't get any place. We hear so much about passenger cars, transportation and so forth. And passenger car, we want to increase the mileage, the CAFE standard for automobiles, from 27 to 35 or something like that. And that's going to do it. Well, if we did that, that might save a couple percent of the problem. We talk about it in the news all the time, and Congress fights over it, the president fights over it, but it's only a couple percent. No more different than our waste. So if that's going to be so big, why don't we do that? What it means is we've all got to do our part, because there's all these different segments, and each one, if we don't have each one addressing what it can do in this area, we won't accomplish anything. And that's the point I want to make. Ours is the waste, and so what can we do about it? So how can we reduce energy consumption and greenhouse emissions from wastewater treatment? And I think this is something new. This is a new paradigm for us. We haven't thought about that. We haven't thought about CO2 in the past. We think about other things. But I think in the future, not when I'm here, but when all you young people in here are going to work in the future, I think this is going to be an important part of your decisions on water and wastewater treatment. So let's look at it. I don't know what's the best thing. There's no way I can stand here and talk to you about all the possibilities. But it's worth just at least showing, some possibilities and what might be involved. And for that, in case you don't know where Stanford University, have you heard of Stanford University? Down there in the bay, next to what we call South San Jose Bay. So I'm going to focus in down there to show you some possibilities at that south end bay. And we have here down South Bay, there's 3 treatment plants, Palo Alto, Sunnyvale, and San Jose. Now, those 3 treatment plants have to, it's pretty stringent down there. They have to do normal BOD removal, and they have to do nitrification, filtration, disinfection. So they do a really advanced treatment before they can discharge. All 3, same discharge requirements. All 3 doing a good job. All 3 designed at different times, different requirements, different thinking, but they all do a good job. And there's no way going to criticize any of them on that. But if we say, well, what if today we want to think of global climate change? And how are they doing on CO2 emissions and electricity? Oh, well, let's kind of look at now. This is not data from their plants. I made up these data. But I took the plants and I said, well, okay, given that kind of plant and given kind of our normal way of operating, sort of the back of the envelope kind of calculations just to get a little ballpark, this is what I came up with. Okay, now first we got to look at doing an aerobic biological treatment like we do here with an activated sludge tank and organisms in there. We blow air in. That air takes power. We go to a power plant and we get the power, say, from some fossil fuels. And when we get the power, the energy, we put off CO2. So not only do we get CO2 from oxidation of the waste in the tank, we also contribute some CO2 from the power plant that's given us the power to run the plant. If we look at the anaerobic wastewater treatment, we put it in, we don't have to put power into it. We just put in the waste, mix it up a little bit with the bacteria, the right bacteria, and they give us CO2 and methane. The methane goes up in the air, that's really bad. But if we capture it and burn it, it'll go to CO2, but at least we get some energy back that can offset this power that we see at the left side. Okay, now let's look at the Palo Alto wastewater treatment plant. They do primary settling, aerobic, BOD removal, like those tanks I showed, nitrification, they oxidize ammonia, takes power, takes oxygen. But then they take the solids that they get, the primary settling and also the waste biomass from the activated sludge, and they incinerate it. Okay, look at that. Now here's a little picture trying to show, say, if we start out with 100 of organic carbon and CO2, I'm just trying to make a carbon balance through here. And this is their influent. Up at the top, we have it liquid and we have it solid. So we think of water and the suspended solids in it. I'll separate those 2 out. In the liquid above, we have refractory organics. So these mean they're sort of humic materials, the stuff that we don't even treat. They don't have an oxygen demand, but there's a lot of it that goes through the treatment plant in the stream and we never sort of pay attention to it. Kind of yellow stuff. I mean, natural, so we think it's okay. And then there's a green shows the degradable part, and that's what we treat in our biological system, that green degradable. When we do that, we create some bacteria. So we end up, this solid part gets a little bit bigger. We get rid of that green stuff up there. And to do the green and get rid of it in our aerobic tank, we use a little bit of power, and this is the CO2 that comes from the power plant. CO2 from it emitted by the power plant. So we're trying to figure that in too, okay? So that's this little pink down here. CO2 is what we oxidize. We take that green stuff and oxidize that, the CO2 comes out from that oxidation. This is the CO2 from the power plant. Okay. Then we go to incineration, and we take all the solids and we burn them. So we get all CO2 out from that. And so what we see is on this scale, the CO2 that comes out is this 90. That's the sort of what this plant's doing. So we went in at 100, and we got some refractory that went out in the stream, didn't do anything, we got that 90. Okay, let's now look at San Jose. What San Jose does different is they go through, but instead of sludge incineration, they digest it. They put it in these tanks, these methane fermentation tanks, and get the energy back. Let's see what that looks like. Okay, it's the same going in. It's the same up to this point. But then we put it in a digester, and we take the degradable portion of the solids, that little light brown, and we get rid of it and make methane gas. And we get some CO2 out too. Both CO2 comes out. So then we take that methane and we burn it for energy to supply this pink. You know, we don't use fossil fuels to get this. We use that energy from there. And indeed, we offset some fossil fuel. We don't, you know, someone else doesn't have to use the fossil fuels. We send them the power. And so we cut CO2 down. So we got CO2 going down because we're taking credit for not using fossil fuels. So the net from this, we see 37 net increase of CO2 from here. And we see a little bit of solid brown between 37 and 63. Now you have to think about that. That material there is refractory organics, like what we put in the stream, the blue. This is we put on the soil as a soil conditioner. And it kind of decomposes. Now, is that bad, or how do we think about that? Well, you can think about it. Anyway, I'm going to say 37, but you can think about that little part. So that's better, right? Now, one plant is an interesting one to me, the Sunnyvale one in the middle here. And I blew up Google. I went down there closer, and I thought this is kind of neat. This is a Google map. I go down closer and look at the pretty picture, mosaic, abstract. And that's photosynthesis in action. That's South Bay. There's all these ponds that are evaporating seawater and goes to all these pretty colors and green. You see this from the airplane, green. This green, and then it gets up kind of brownish, and then red as it gets more concentrated, and different kinds of algae and brine shrimp and everything growing and turn it red. And then when it evaporates, we get the white up the top. So that's, most of that is just solar evaporation of pond, a lot of solar energy. Interesting down there, if we look at it, way down this corner, this little green, you can hardly see it's green, and this guy, that's green as well. And that little piece is the stabilization ponds, algae ponds used in Sunnyvale to treat their waste. That's treating waste from about 100,000 people. And the reason I like to show that little piece is I think we could treat the whole Bay Area if we wanted to do that with all these salt ponds, turn them into algae ponds for waste treatment. Anyway, no one will ever do that. But anyway, I just want to show. So let's look at the Sunnyvale wastewater treatment plant. Okay, there's the stabilization pond, the great big thing. The heart of the treatment plant is Sunnyvale is there. You see it? And we'll go look in it a little bit closer. There it is, and I'll show it. The influent comes to primary tanks, get the solids out, and then what goes out, the soluble BOD, goes to stabilization ponds. After it's treated there by the algae, we come back, and now we get grown algae. We got to separate those out. So they have flotation tanks to separate the algae. The water then goes to these filters, nitrifying filters. And then after filtration, it comes to a filter plant to remove any suspended solids so that we can disinfect it. And then we go out and they have effluent, and we got a wonderful water that we've reclaimed that can be used for essentially any agricultural purpose. We've reused the water by this. Actually, all the plants do this kind of quality. But what happens to the solids that are different here is we do get the solids from the primary tank that settled out. And also, they take the floated algae, the algae they produce, and send them to the digester. What's digested could produce the CO2 and methane, and then when we get through, there's residue that's left, good stuff goes to drying beds, and the farmers take it and put it on the fields for agriculture. So what they've done at the plant is we have this waste coming in, they produce good reusable water, we produce energy, and they produce fertilizer. So we have used this as a resource recovery. Now let's look at this. Now let's look at what has happened in the algae plants. You have to think about that a little bit. So I made this picture. Now what we have in the after primary settling, what we have is soluble BOD, biochemical oxygen, that's organic matter. And I'll just use this formula. It's got a little nitrogen in it and so forth. And that's soluble, doesn't settle out. Normally that's what go to activated sludge plant. Here it goes to the algae pond. In the algae pond we got sun shining, algae, and so the algae take CO2 and water and ammonia and synthesize it into algae cells. It makes cells. And in that process they produce oxygen. That oxygen is used by the bacteria to oxidize this and make the CO2. So it gets the thing spinning around. So what do we get? We go in with soluble BOD, and we come out, same formulas, same thing, only it's particulate now. So all that sun's done is made the soluble material into particulate material. Now that's good for us because we can settle the particulate material and feed it to the digester. So the soluble is kind of hard. It doesn't, we don't make digesters for that. People have been trying to do that. But we know we can take it concentrated in a particulate form and do it. So that's one thing. Okay, so what happens if we look at the algae ponds then? We don't have any energy used in the degradable BOD going away, green stuff, so we don't have that little pink bit down here. We grow a lot of algae. More algae. We send those to the digester, so we get all this soluble BOD and make it in particulate, so we feed a lot more to our digesters, get a lot more methane gas, and consequently, when we burn it, we get a lot more credit for it. So we only got 15 going out from this treatment system. Now these algae ponds, I'm just saying here, I'm up here, Bill Oswald here at Berkeley is responsible for all these algae ponds in California. And he was the champion, he studied it. He's the one who really pioneered this, and we find him in a lot of places. And so I think when you look at this, poor Bill passed away last year. Last year it was, about last year. And, but we owe a lot to him for the work he did, because he always had this in mind, but he was a little bit before his time. But the technology developed is there. This energy crisis, 1970, we worked together with many times trying to do something here. I was working on the anaerobic digestion, he was working on the algae. I was putting them together, right? Working great. Well, these are the gas engines at Sunnyvale that they use to power these with the gas from the digesters, driving the electric generators, which they then can sell the energy. The gas engines are also have to be right next to two big solid waste dumps. So they pump in the gas, methane from the solid waste. They get the methane from the digester, they put in this, and they burn it and put it back onto the grid. So they're using their waste and making energy from it. And back here we see heat exchangers, and they use the heat from that, the cogeneration, to heat the digesters. And right now they have an excess of heat. If you had some idea of what they could do with that excess heat, they've got some down there. But most of it, they put it into electrical energy. Okay, I want to point out a little other part of this. And I mentioned they have an obligation here to do nitrification of the ammonia. Because if you put it in the bay and it gets oxidized there, it'll consume oxygen. So nitrification, or at least ammonia removal, is required. But let's look at these algae ponds in another way for the nitrogen. Before I just showed the soluble BOD, but actually out of the primary tank we also have extra ammonia, comes from our urea. It hydrolyzes, forms ammonia. maybe CO2 if we can get that from someplace, which we have a lot of places for it. But if we put in not only this, but this into the pond, so we have a lot more food for the algae to grow. Instead of 1 unit of algae, we'll get 2 based on this. So we get more algae by that nitrogen. And that goes into more cells. That goes into more biomass. That goes into more energy. The other thing that happens in Sunnyvale during the summer, when the sun is really shining and this whole process works, they don't have to nitrify anymore because they run out of ammonia. They use it all. It's all taken up by the cells. So that saves more power, saves more oxygen, saves more N2O. And so we get another big impact by growing the algae from this part. Now, so what I did here, don't want to bore you with all these numbers, but I was trying to do the back of the envelope calculation, taking a typical wastewater characteristic and took these treatment processes and looking at the CO2 equivalent thing from 10,000 kilograms per day of BOD. Well, that's about what you get from a population of maybe 200,000 people. Okay, so Sunnyvale is about 100,000, so it's a city twice that big. And this would be 1,000 kilograms a day. It's about a metric ton of CO2 equivalent. And we'd get from the Palo Alto plant, aerobic incineration, about 29 metric tons per day. With aerobic and digestion, we cut that over in half to only 12. And with the algae, 6.2. So the point here is we make a big difference on the kind of design we have when we want to look at it in terms of CO2 production. And if we look at the energy cost for these different plants and just working out about 10 cents per kilowatt hour, Palo Alto, I mean, well, actually, this is a bigger city than Palo Alto. This is about 200,000 people. It would be cost about $236,000 a year that they'd have to buy in energy to run their plant. Well, at Sunnyvale, I mean, with San Jose, because of their digesters, they'd get about $97,000 back in credit at 10 cents a kilowatt hour if they can sell it to that, so get that. They use some of that energy, other energy, for other things on their plant rather than just aeration, but that's part of that. And if we do the algae digestion and get all that extra algae, get about $366,000 back in energy. So not only are we saving CO2 and cutting that down, we're saving on energy, we're making money in the process. Oops, I want to go back and show one thing here. I put a penalty on here, CO2 penalty. And I just want to do a little thinking here because we hear of this tax, CO2 tax, talk about carbon tax, so forth. Congress thinking of it. We have a global trading system for carbon right now. It is about, I have this per ton of carbon, it's only about $4 or $5 now trading on the world market. It's not a big market, it's not that expensive. If we're going to start really thinking about doing this, US, now they're talking, Congress is talking about doing this, putting a little bit of charge on it, you put CO2 in, they're probably even starting a little bit lower than that. But if we get that started and it goes up, it's likely to go, if we get serious, start getting serious, go up to $20 a ton. And the people, the government panel said, if we really get serious, with this, that's got to go up about $200 a ton. If you're going to really force people to think differently about what we do. And boy, if it goes up, I just put $20 a ton, and I just wanted to show you if you put a penalty of $20 a ton for the CO2 emission, this was the impact it would have on the bottom line. $58 of the 236. So, could get you thinking about it. At least it would fit into yours. If it went up to $200, you can see that that's going to be the major driver behind what you do. So I just wanted to see where that fit into our overall thinking. Well, anyway, I just want to here, in conclusion, just say that we need to reevaluate waste treatment alternatives because of climate change concerns, something we need to do in the future. And the other thing is methane, the bad methane that we let emitted now, we've got to contain that because it is an important component. We've got to think about septic tanks and sewers and certainly landfills, and we're putting a lot of attention into that now, but we've got to do more. Desired alternatives are those that reduce both the greenhouse gas emissions and power consumption. That's what we see the direction they're going. And I think the anaerobic treatment, which I always liked in the past, thought was good for this. Maybe we'll do more about it in the future. Certainly California, most of our treatment plants in California, we do it. Some place in the country, they frown on doing it. I don't know why, but they have. And we've got to think of that more on our industrial waste in general, too. And one other point is wastewater is a resource. We can't think of it. In fact, in Singapore, which they're doing a lot on this, in Singapore, they don't call it wastewater, they call it used water. And they look at it as a resource for water, energy, and nutrients. And that's the way we have to look at all our resources and get as much out of them as we can. And I'd just like to finish off with another Rene Dubos quote. He's always so good at putting quotes in four words, or quite that. But this one I heard him give a talk at Caltech back probably in the late 60s or early 70s. He goes, trend is not destiny. So he's an optimist. And what he's looking at, we have all these trends. We see all these, I mean, we're projecting climate change. We see, oh my God, you know, sea is going to rise 3 or 4 feet. We're all going to be inundated. The Bay Area is going to be washed out and so forth and so on. I don't know if that'll come. I won't be around to know whether that is destiny or not, but Dubos said it's not destiny. But what he meant with it was something else. I like someone else who said similar to that a long time ago, long before Rene Dubos, because he wasn't the only one that said it. It's an ancient Chinese proverb, which I like. And it says, unless we change our direction, we are likely to end up where we are headed. And where we are headed doesn't really look good. And I think what Rene says, you know, it doesn't have to be our destiny, and it doesn't if we change our direction, if we all make our effort, if we think about this in the future. And I think that's really what this is all telling us. We're part of it. Like Pogo, we've looked at this, thought the enemy, and he is us, you know. So we have our part. It's going to create a lot of problems for us, but we're also creating the problem. And so if we complain about the one, we've got to do our part to do the other. It's small, but everybody has to do their part. And I wish I had 50 years of great fun in dealing with hazardous waste and all that kind of pollutant stuff, and where are we going, and wastewater reclamation. I think the young people here now got to be interesting to see 50 years from now. I wish I could be down and look at you and see how you address this, or whether you are inundated, as the saying goes. Anyway, thank you very much for your attention.
I'm pretty sure Perry will answer questions. Could you repeat the question, because we are taping that, so this stays for...
I will try.
That's what I was wondering. Could you show us that slide again where you showed how much CO2 is produced from cars and how much from wastewater treatment?
Well, I shall try to do that, if I can figure out how to get out of this thing here. End of slide, click. Okay, here we go, this. You're interested in oh, we top up.
The
There,
question
this one right
was
here. That's-
how much CO2 is produced from cars and wastewater.
That one?
Yeah.
Yeah.
So wastewater is 3%, cars 8.7%.
Yeah, that's total gasoline in cars and total waste. We're putting the notes down. Okay. Someone else? Yes.
I've got one small clarification question and then an opinion question on denitrification. One of them, the first one is when you showed the nitrous oxide and the methane and the CO2 as being 8%, 15%, and 77%. Is that in carbon dioxide equivalents?
And you're talking about the one slide dealing with the biological conversion slide, starting with organics and going to methane?
It was before that. It was an introductory one showing how much emissions.
Oh, well, okay. What's your question about that? Let's see if I can find that.
the numbers of the methane and nitrous oxide being about 25% of the emissions. I was wondering if that was in carbon dioxide equivalents. I just missed that. 24. Right there, number 19.
19. This thing jumps around there. 19? That one. Okay. What was the question on?
Is that in CO2 equivalent?
Yes, that's in CO2 equivalents.
Okay.
Yes, yes, yes.
And thank you. And the next question is, in many places in California, wineries and food processors apply their processed waters onto land. And we did a little research project on that. This is high BOD waters with high nitrogen, and put some panelized cylinders into the ground, and we saw that it doesn't take far into the ground to get to anaerobic conditions. The BOD consumption in the soils greatly outpaces the re-aeration of oxygen into the soils. So we see iron and manganese leaching, we see all the nitrogen disappear very quickly.
Right.
In these extremely anaerobic or these anaerobic conditions, are these land processors or the land applicators of processed water, are they releasing a greenhouse gas or wonderful gaseous nitrogen?
Well, as it goes down to the ground and goes anaerobic, you will get, as I showed before, you'll get methane. You will get methane. And the methane will be there under anaerobic conditions. Now you're down in the ground. If the methane then escapes to the atmosphere, it's a greenhouse gas, bad one. Okay. As it goes through the soil, if there's oxygen, if it passes through an aerobic zone where there's oxygen on its way out, the gas out, and if there are methanotrophic bacteria that live on the methane and oxidize it, it'll be oxidized to CO2, and it won't go out. And one of the questions that we would have on any case, even septic tanks, and you know, with these estimates on septic tanks are based upon some assumptions, which are pretty, and some nitrous oxide. We really don't know. If someone wants to do anything, I think good studies on this. How much of the methane escapes from the soil, in the case you're talking about, or how much is oxidized within the upper layers? Pretty hard to say. I don't know. We know some of it will be. And that's the same thing in lakes where we have anaerobic bottoms in lakes. Down below, when methane comes out, we see it bubbling, go to a little swamp, we plug it and bubbles come out, that's methane. If there's enough of a layer of oxygen and the right temperatures and so forth, it could be oxidized before it gets out. So some portion probably is and some portion probably escapes. That's a long answer.
I may have just misspoke, but
okay.
I was concerned about the nitrogen. Is it?
Oh, the nitrogen, not the methane.
Right.
Well, the organic was brought up a good question because the methane you got to worry about too. Okay, the nitrogen, if you get, generally what happens in a soil system is that ammonia sorbs to clays up in the upper part where it's oxygen. Then water comes down and you get some oxygen there, so the ammonia gets oxidized to nitrate. Nitrate doesn't hold the clays. So water comes down, the nitrate gets purged down. Down below, the nitrate then, if it hits anaerobic where this organic is, and it goes anaerobic, the nitrates will be converted mostly to nitrogen gas, but some of it to N2O. That's the biggest source of N2O. Now, it's possible that that gets oxidized in the soil, but that's where a lot of it gets out. And in agriculture, if you look at agriculture was pretty big. And the manure, the nitrous oxide was pretty big. And all that's because of the nitrogen contained in those wastes, going in, like you're saying, some of it through nitrification, denitrification, is coming out as N2O. So that's a big one. That's a biggie. And you would have to worry about it. The thing, if you look at the data in the literature, it's pretty confusing. The assumptions I have in N2O that they're making, the EPA's making, the IPGG, the PCC making, they're all assuming a certain number, but that number's off by in both directions by a factor of 10 or more. We don't have enough data to really get a good handle on that problem. Some of it escapes from rivers and so forth. So it's something we need a lot more data on to really know how serious it is. Okay.
I think there's a good argument to be made that the CO2 emissions. Thank you. I think there's a good argument to be made that the CO2 emissions due to biodegradation at the wastewater treatment plant should be considered carbon neutral in the sense that their source is mostly the food that we eat, so it's CO2 that was originally taken up by the atmosphere. So I was just wondering if you had an opinion about that. Like if you were asked to, set the carbon tax rules, would you argue for that CO2 to actually not count as carbon that you would tax? In which case, treatment plants could end up coming out ahead.
Sure. Yeah, what Kara is indicating is that in all the estimates they take this carbon dioxide that I mentioned from organic oxidation. They assume, well, that organic was food, and with part of the natural cycle, algae produce it and so forth. It's not produced from fossil fuels, so we shouldn't be penalized for it. I put it on. Now, they do penalize you for the methane. I mean, the methane that they say, well, that's natural organic matter too, but if it goes methane, that's bad. If it doesn't go CO2, it's okay. Well, I think my own feeling is this, that in our counting, we need to count it all. And let's make an analogy. Let's think about this a little bit. And I don't know the answer to this, but it's something that's puzzling me, so I'll throw it out to you. You got the young people, they can puzzle it over and think about it. We cut down forests, and we make newspaper, right? And then we take the newspaper and we recycle it, which is good. We may burn it or something like that, but there it is. If we took that newspaper and we went out to all these mines in Nevada where it's dry and never rains and got big holes in the ground, and we took all the newspapers and stuck at that, we'd be sequestering that carbon. Now, what they're talking about is power plants to burning fossil fuels and going through a terribly expensive process to try to capture that CO2 and put it and pump it way in the ground. I said, boy, that's expensive. If I took a ton of paper, which I can collect from all of you and put it in a truck and take it out and stick it in, I've accomplished the same thing, and it's really cheap. Now, so that's the same thing you're talking about. So that's a cheap way of doing it. I said, well, okay, how about trading? You guys in the power plant, don't stick your stuff in the ground. Pay me, $200 a ton, and I'll take my newspapers and collect them from you, Boy Scouts, and collect them for us, give them some of it, and we'll bury it. And we accomplish the same thing, cheaper. Now, is that better? I don't know. Then we can grow our forest fast. We'll go to a place that is marginal for forest. We'll go a lot of forest. We can make it into paper, and then we can bury it so we can sequester it. And that pulls the CO2 out of the atmosphere, which is good. Someone's offering, multi-million dollars if you come up with a scheme for doing that. But we could do that and bury it. So it's how do we deal with that in the balance? I don't know. I know right now they're calling it carbon neutral. In other words, if they're looking at a penalty, you don't want to penalize it, and I don't think you should penalize it. But maybe there's ways that we can think about that when we think of carbon trading. And that's part of it. Carbon trading, if you do the animal manures and make methane out of it, get energy, you get paid for that. And we get paid for taking the landfills and getting the methane out of it. We get paid. So, people are thinking about, gosh, that comes in. We get paid for doing a lot of the things we're doing now. And we don't get anything with it. So I don't know quite how to think of it. Economists have to bring it in. But, it's an interesting balance if we really get serious about it.
Well, we should have more forms to fill, and all of them in quadruplicate.
Well, by one thing, it's algae. These algae ponds, the energy they're getting from that, they get 10 times more energy per acre with algae than you do if you convert corn into alcohol, stick it in your automobile. You get 10 times more from those ponds. So we got all that bay, rather than destroy all our agricultural land. Okay.
Hi, I'm curious for the energy comparison you had across those 3 plants, if Palo Alto practices some sort of heat recovery off their incinerator, and if they did, if it would bring the comparison closer.
Yeah, that's, if Palo Alto, the question was if Palo Alto got energy from their combustion, then they could offset that. That's true. The problem is they can't get the sludge dry enough to get energy out of it, and indeed they have to put energy in. They have afterburners that they add energy to it. So my my balance didn't show that part. So you'd have to get it a lot drier, and getting drier takes a lot of energy again, and so forth. So there's a balance there. But right now, they're not getting out, they're putting more in. If you could figure out a way to get it out, that would be useful.
Hi, thanks for giving this talk. My question concerns, I guess, the growing use of like antibacterial cleaners and soaps, and how those affect or may affect the aerobic or anaerobic bacteria that are used in the digesters. Or I guess the aerobic ones are not in the digester.
I'm sorry, I didn't catch the question.
How has the increased use of antibacterial cleaners and soaps affected the treatment of water by the anaerobic bacteria?
Okay, that's a good question. The question is, how do our antibacterial components in detergents and so forth we do in affecting the treatment plants? As far as we know, they're not causing any harm. Most of the treatment plants now, with their keeping hazardous industrial waste out of them, seem to be doing pretty well. I think there's probably enough dilution that they aren't harmful. So I don't think we have any evidence that they're really harming the treatment plants. I don't know if anyone else does or not, but most of their treatment plants are running pretty well, and I think they all get about the same. So I'd say they're probably not, at this stage, are not adversely effective on the treatment.
Thanks. So to somewhat piggyback on that question, I understand that in wastewater treatment, things such as caffeine, hormones, drugs are not really filtered out. Has there been any research done about maybe algae or bacteria that could filter some of that out of the water?
This concerns with what we call pharmaceuticals and personal products. There's a lot of concern about them now today. As we move through, I've been looking at hazardous chemicals over the years, and we find out there's a lot of new materials. Many of these are not degraded biologically and are present in the effluent. So there is concern about them, and David Sedlak here has done a lot of work on it, looking at from wastewaters and different treatment processes. Yes, there are a lot of concerns about it. Some of them biodegrade, but there are some that are persistent. So we know bacteria attack some of them and not others. And there are others using other kinds of treatment processes, like sorption, for example, or like some kind of advanced oxidation state to get rid of them. Reverse osmosis does some too. So but there's a lot of concern about them. And it's like many of those, we don't know their environmental impact, and we still need it. So, the problems I talked about, the old problems, they're still with us. The problems of persistent organic are still with us, and they'll go forward. Now we're just adding another one to it. But there has been a lot of work done on it, and still is, trying to address that question. Important question.
I do take to heart your admonishment to think globally and act locally, but I do want to ask, I know you've been working in China quite frequently, and wanted to find out the state of the dialogue there with regard to waste treatment, greenhouse gas emissions, climate change. Could you speak to that, please?
Well, China is developing very rapidly, as we all know. They're having mammoth environmental problems. And generally, when you go and talk to a country like that, they, well, a number of years ago we had a committee that tried to convince them that it's really bad to contaminate groundwater. Because in the United States, we contaminated our groundwater, and we're now spending close to $1 trillion trying to remediate it. And the thing is, you contaminate groundwater essentially forever, because it just persists. It's not like a stream flushes out. And they said, well, that's all right for you to say, but we've got to develop first. We need an economic base. And it's true, a developing country needs an economic base to get good drinking water and so forth. But they've gone too far in their economic development without coupling it with pollution control. And they're really facing a major, major problem in China, and all the streams included. So at this point, I'm sure CO2 is the furthest thing from their mind, because they've got people dying and animals dying and displacement and a huge uproar and protests going on around the country. So they're beginning to put a lot of money. They know that's a big problem, and so they're facing that. Now, we know that they're passing us up on carbon dioxide emissions. My own feeling on that is this: they're not going to do anything on that problem. They got big problems to deal with the money they have. We've got CO2 problems. We don't do anything about it. We say it's not a problem. Why should they? I mean, we're the leaders. We got the money. We got the resources. We've taken care of the problems that they've got to face now. Why aren't we leading the pack and saying this is a problem and learning how to solve it and how you would do it and how you move forward? Why should anybody do it if we don't? We, the supposed leaders, don't do it. And that's the big problem. Until we do it and really make an effort and say it's important and that we've all got to do it, we've got to all work together to do it, no one else is going to do it, my feeling.
Okay, any more questions? There's open mic with Perry. Well, if not, then thank you very much.
Thank you.
I appreciate very much your talk.
Good luck to you all.
And again, a reminder that December 4th is the last of this seminar colloquium, and you are all welcome to join us at that event. Thank you very much for coming.